Now we'll go to the final stage of this absorption emission spectroscopy, where we will talk about rotational of hydronic transitions. So, to understand this, we'll just tell this and then we'll go to the rotational fine structure. We have already considered the hydronic transitions. So if you have, let's say, one electronic state, another electronic state, say epsilon double prime, epsilon single prime. Now here you have D double prime, say 0, 1, etc. Here you have D single prime as 0, 1, etc. Now from here to here, so we have seen that from here or from here to here, we get the lines which are called progressions. They are hydronic lines. That means you have the simultaneous transition, the electronic transition, but each transition you have slight difference in energy because you can go from one vibrational state to another vibrational state, and that's why you get a kind of band. So we talked about branches. Say when we had this, so now we will see what will you get when you have this accompanied by the electronic transition. Now you think about that. So we have learned the vibronic part. So you talk about the progressions. In addition, you remember that we already talked about, say, if you had like J, say double prime, and here also you have J single prime. So J double prime as let's say in this case you have 0, 1, 2, etc. Here also you have 0, 1, 2, etc. Now if you have a transition over here, remember, same vibrational, same electronic state, different vibrational state. You have one vibrational state to another vibrational state, but different rotational transitions. That we have already studied. But they belong to the same electronic state. But now we are trying to do the same thing when you have the vibronic transition. So you go from one electronic state to another electronic state, one vibrational state to another vibrational state. But now, for each progression line, we want to see the rotational fine structure. Okay, so now in this case, I consider this as my J double prime, this as my J single prime, 0, 1, 2, etc. So for a specific line, like here you have the 0, 0 line, here you have the 1, 0 line. The 0, 0 line actually is composed of several lines, and that will give you basically the rotational fine structure of the vibronic transitions. So let's talk about that. And we know the transitions, the intensities are governed by the Frank-Condon principle. We will see the line positions and what are the other aspects. Now, remember that for delta J 0 plus minus 1, that is the selection rule. But I told you that J equal to 0, like J double prime equal to 0 to J single prime equal to 0, like this transition is not allowed. So delta J may be 0, but it cannot be 0 to 0. It may be 1 to 1, 2 to 2, etc. But this is 1, and delta J 0 is not allowed when you have omega equal to 0 to omega equal to 0 transition. This omega, I told you L plus S, the Z component. That means if you have a singlet sigma to singlet sigma transition, the delta J is not equal to 0. That means in this case, only delta J plus minus 1 is allowed. So keeping these specific selection rules associated with the bichronic transitions, what are the rotational transitions? So we can now write down the line positions. Now at this stage, let me tell you that delta J 0 plus minus 1, that means delta J is minus 1, 0, 1. That means this would be P, this would be Q, this would be R. That we have seen. Minus 2, plus 2 also, O, P, Q, R, S. Because minus 2 plus 2, they will come in the corresponding Raman transitions. That we have already seen. So, in general, suppose it is only the row vibrational transition, no electronic transition within the same electronic state. So, what type of behavior did you see in P and R branch? Can you tell me? What did you see in the P and R branch?
Sir, when J increases for the P branch, the gap decreases and they become crowded. And for R branch, when J increases, the gap decreases and means they become widely spaced.
Gap decreases, forms the head, then goes back towards the red side with increasing gap. Okay.
Yes, band. Yes.
So you get the band head formation, and that is in the R branch. Now you can see, obviously you would expect the similar behavior here, but you can get the opposite also, which was not possible for pure vibrational transition within the same electronic state when you talk about the rotational fine structure. But in this situation, this is possible. Okay, why? Because you remember our main say consideration which gave us that. Can you recall that what was the main consideration which gave this different behavior for R branch and P branch lines? Do you recall what was the consideration which gave us this behavior?
We consider that both have different P values.
Yes. You consider the rotational constants are different. Now, what was the difference that we considered? Which one is larger?
For lower state, it will be larger. For higher state, it will be smaller.
That means B double prime was larger than B single prime, because the bond length is larger in the excited state. Okay. And there is inverse relationship. That was the consideration. Yes or no?
Yes, sir.
Okay. So in general, here also you will see the similar feature, but you get the reverse behavior also in certain situations. Suppose if you have the electronic transition from an antibonding orbital to a bonding orbital, that means your E double prime corresponds to an antibonding orbital, whereas E single prime corresponds to a bonding orbital. Okay. Like for oxygen, the HOMO electrons are antibonding, isn't it? Oxygen molecule. Hydrogen, you have 2 electrons both in the bonding orbital. But for oxygen, the HOMO electrons are where?
Pi star.
What? Pi star. That means antibonding orbital. Now, suppose if you have the electronic transition there, and you take them from pi star to somewhere in some pi or some sigma, that means you are going from antibonding orbital to a bonding orbital. So in general, what will happen, the bond length, because bonding orbital means it is a stronger bond, so a shorter bond. So although you have the excitation, but this is electronic excitation now. So vibrational excitation is accompanied by electronic excitation. So on excitation, the bond length will decrease. Do you understand? So you get a special case now. And if the bond length decreases, so your excited state rotational constant will be more than the higher than the ground state rotational constant. Is it okay? So if you apply your common sense, what will you see in the corresponding spectrum about P and R branch? So now you will see the situation would get reversed. R branch lines should be widely spaced, P branch lines should be, say, closely spaced, and a band head would form in the P branch, and a band would, say, in one case the band would have the tail towards the red, in another case the band would have the tail towards the violet. So we call them that the band is degraded towards the red, and here we call band is degraded towards the violet. Is it okay? Do all of you understand what I meant? So if you talk about the pure rotation vibration spectrum, we have seen. But if you see the rotation vibration structure of the electronic transitions, then you have the probability of getting both. Like both, you can have head formation in the P branch, you can have also in the R branch. Obviously not for the same transition. For the same set of transitions, it may be either in the say P branch or in the R branch. It will be in the P branch only when you have the transition from antibonding orbital to bonding orbital, so that after transition, previously we considered that the centrifugal force would be more and the bond strength will be more, but here the electronic effects will dominate, and you are going basically from antibonding to bonding orbital, so bond length would get compressed, and you get the reverse behavior. Is it okay to everyone? Do all of you understand?
Sir, can you again explain the oxygen case, that how the bond length can be shorter?
Not necessarily oxygen case. Any system, let's say you are taking an electron from an antibonding orbital and going to bonding orbital. That is your electronic excitation. Okay? Like in this case, suppose if you go from 2 pi star is the HOMO, from let's say 3 sigma, 3s sigma orbital. That is the corresponding electronic transition. But here, what you are doing, you are taking from antibonding orbital to the bonding orbital. That means the bond length will decrease. And the corresponding effect you can see in the corresponding vibration rotation spectrum. Because the rotational constant for the final state would be now, say, because the bond length has decreased, rotational constant would be more, and accordingly, all the analysis would get reversed. Is it okay?
Yes, sir. Okay.
Okay, now let's see. We will analyze. The first, I will not write it again. Say E total is E electronic plus E vibrational plus the rotational is B bar J into J plus 1. Okay, these are all centimeter inverse. So delta E is in this case delta E of this, so which I can write delta E V single prime, V double prime. That means I am taking any specific vibronic line from the, say, vibrational progression plus delta of B bar J into J plus 1. And here now we will apply the selection rules. We will find out delta J. First we will see plus minus 1, and then we will also see 0 for the Q branch. And we know when the Q branch will appear. Q branch will appear only under certain conditions. So that I have already told you about the selection rules. So can you very quickly find out only difference, whatever you have done before, only difference you have to add this. So this tells you that this is the only extra part what you have to consider. Okay, can you tell, previously it was just delta V, now you have V single prime, V double prime. This refers to the position of a single progression line. Now we are talking about various possible lines, which was considered to be one single line in the vibrational progression. Now each line is basically composed of several lines because of the rotational fine structure. So you find out very quickly and tell me the results. So you first tell what is nu bar P. The first is delta E V single prime, V double prime plus what? This we have already done. Okay. Then nu bar R and also nu bar Q. You tell me very quickly. And you remember we discussed that P branch lines are denoted in terms of J single prime, whereas R branch lines are denoted in terms of J double prime. And for Q, anyway, delta J is 0, so J single prime is same as J double prime. So as you did it before, you should not take much time to do it. Okay, let me just tell you important aspect. Say about your final test. It would be on the same day and same time, which was announced before. Okay. Do you recall when it was announced, which day and which time?
The 12 April.
At least one of you just respond.
12 April.
Hello?
Hello, sir. April 12.
April 12th, usual class timings, isn't it?
Yes, sir.
April 12th, usual class timings, and your syllabus would be whatever was taught before rotational spectroscopy will be out of syllabus. Rest, everything would be in the syllabus. Okay, tell me what is there for these P branch lines? This is the expression we already did. Only thing here you had only the vibrational energy difference. Here you have the electronic vibrational energy difference. The rest is same. What is the expression? Don't take that much of time. Tell me, you check your notebook and tell.
Sir, in vibrational part, there are 4 terms, and in rotational part,
You talk only about the rotation. Vibration, you are talking about specific vibrational level to another specific vibrational level. Then we want to see the rotational fine structure. So this part is only for one progression line. Don't bother about that. That we have already discussed. Now we see only the rotational part. Tell me the rotational part only.
the rotational part for P branch line is J prime plus 1
What?
into J prime plus 1 into the B bar prime J prime minus B double bar prime J prime minus 2 B double bar prime.
No. We wrote it like J prime plus 1 in something into J prime plus 1 plus something into J prime plus 1 whole square, isn't it? We wrote it that way.
Okay.
Yes or no? I recall that's the way we wrote. Similarly, for R branch, you wrote that it is something into J double prime plus 1 plus something else into J double prime plus 1 whole square. So tell me that result. Don't take that much of time, then I will not be able to tell you what I wanted to tell extra. Is it the correct expression? Check. Check the signs. Is it okay?
Yes, sir. For P and R branch line, these were the equations.
And here the same thing, only J single prime is same as J double prime because delta J is 0. Anyway, you check it. You know how to do it. Even if there is some sign mistake here and there, you check it. So you can see that P and R branch lines. You can write it delta PR as this. I am writing some A. So A minus prime plus B double prime M plus, let me put plus B prime minus B double prime M square, where M can be plus minus 1, plus minus 2, plus minus 3, etc. Where all plus signs corresponds to R, all minus signs corresponds to P. Is it okay? Can I write this in this form, these two? Yes or no? You see, if I put here 0, 1, 2, etc., I get this expression. Similarly here, I get this expression. Is it okay? And this one also similarly we can write mu bar q as some this also, let's say I write this as b plus bar minus n plus n square, and here also your n can be 1, 2, 3, because delta j 0 is not allowed, so it can be only 1, 2, 3. So you can see that we have simplified the expressions and written in this form. Okay? So we didn't do anything, just simply we have just written it in a simple form. That's it. But suppose if I ask you, if I say that m is a variable, what does it signify? If I want to say that this, let's say, is a function of m, Is the equation of what?
The equation of parabola.
Okay. This is also a parabola. Actually, this was first analyzed by Fortrat. So this is called Fortrat's parabola. Now, if I see this parabola, nature of the parabola, and if I take the general case means your B single prime, so excited state, bond length is more, so excited state, rotational constant is less. Then the picture would be, suppose if I say M or N versus nu bar P Q R, then you will see that it will go like this. This is up to this point, you have nu bar R, and here you have nu bar P, and you have another like nu bar Q. Okay, so nu bar Q will end here. And because here this line corresponds to M or N0, and we have seen none of them can be M0, so there is no point from this curve or this curve, they are all parabolic curve from, and there is no negative side for Q, so it ends here. And positive, negative, like positive part is for R and negative for P. So if you have this situation, then you can see the head is formed over here in the R branch. And where exactly, you see that if I can find out which M or N the head is getting formed, from there we can immediately find out what is the corresponding J value. So around which J the head will be formed. So how to get this? You take this curve, parabolic curve, and the vertex of the parabola you have to find out. How will you find out the vertex of the parabola? That's the maximum value of y over here. If you write y as a x square plus bx plus c, this maximum value of this is over here. You cannot go beyond this because this is the y I am writing over here. So what do you get is d nu bar p r by dm, put that to be 0. Okay, that gives me this point. This is the vertex of the parabola. From there, we can find out where exactly the band head is going to get formed. So, tell me the result. You put it over here, take the derivative with respect to m, put that to 0, and tell what is the expression for m you are getting, where the band head will be formed. Tell me very quickly. What do you get?
Sir, M value is B double prime plus B prime divided by 2 B double prime minus B prime.
This one?
Yes.
Okay. So now see the general case. General case, which one is larger, this one or that one?
General case is B double prime larger.
B double prime is larger. That tells that it is a positive quantity. M is a positive quantity, isn't it? If it is larger, this is positive and this is anyway positive, so M is a positive quantity. M positive means which lines? R lines that we have seen already, isn't it? So what it says that the band would be towards the R branch, the tail would be towards the red, and we say that the band is degraded towards the red. But suppose we talk about the special situation when you have the transition from antibonding to bonding orbital and bond length will decrease after excitation, then this would be B double prime would be smaller than B single prime. Yes or no?
Yes.
That means M becomes negative. So now the head would be formed in the P branch. P branch means towards the red side. That means the tail would be towards the violet side. And we call the band is degraded towards the violet. And not only that, I can calculate the exact value of M, at least nearby the integer. And M is what? Either J single prime plus 1 or J double prime plus 1 that we have already seen. So from there we can find out which J to which J transition will give the actually the head formation. Okay? Do you understand, all of you? So in order to understand the rotational fine structure of vibronic transitions, in fact, the most clever approach is through the Court's parabola, and that will give us all information regarding the rotational fine structure, head formation, which side, which specific rotational transition will give us the head formation. Remember, now for any vibronic transition that we understood in terms of the vibrational progression lines in the corresponding electronic transition, each line would be composed of several lines due to associated rotational transitions, and they will form the heads and the spacings, everything, and we can find out the heads for each and say individual vibrational typical vibronic transitions, and we can analyze this to get information regarding say the bond length, say strength of a bond, everything. So even for the molecules where we don't see the pure rotational or pure vibrational spectroscopy because of the selection rules, they are not obeying. So in that case also, you will see, as I told you, that all electronic transitions have cross selection rule allowed. So it doesn't matter whether it has a permanent dipole moment, whether the dipole moment is changing during vibration, etc. Those questions will never arise, and you get all rotational and vibrational information from the corresponding rotational fine structure of the vibronic transitions. Okay, so now I stop at this point. So we'll go to another type of spectroscopy. So you remember that what we started with a two-level quantum mechanical problem. So you go from one level to other, and we analyze thoroughly how we can go for this absorption emission type spectroscopy. But now, suppose we think about a situation where you have the energy levels which are degenerate. If you have a set of degenerate energy levels, can you make that particular system amenable to spectroscopy? Because whenever we talk about spectroscopy, obviously there's a question of inherent associated transitions. Because the energy levels are having same energy, so question of transition per se doesn't arise unless you lift the degeneration. So people started thinking that, okay, first you lift the degeneracy, create a system with energy levels which are separated now, and then you apply the standard absorption emission technique. And obviously, so if you apply some external field, interact with them, and see that you have the energy levels are getting now separated, and then you apply the absorption emission spectroscopy rules. So what it says that the frequency required, the frequency which separated these lines, depending on what is the frequency or the field strength applied over here, that will determine how much is this gap. And then when I apply a secondary radiation field to have the transition, that frequency and the previous frequency, they would go in tandem. So if you start with a very high such frequency, the gaps would be much larger. You require a higher frequency, higher energy to cause transition, and so on and so forth. And that is the reason these spectroscopies are generally called resonance spectroscopies. Because there is a resonance between the two types of frequencies just now I mentioned. So first, and these are very common in case of the spin-related spectroscopies, which we didn't touch per se. So if you start with a set of levels where you have a specific spin, let's say suppose if you have a nucleus of spin capital I, then you know for each I there may be 2I plus 1 number of Mi values, and all of them will have the same energy in absence of any external field. Similarly, if you have some electron spin capital S, then you have 2S plus 1 number of Ms values, and those two S plus 1 number of spin states, again they would be degenerate. Now, if you apply some external magnetic field, they will interact in a different fashion with although in absence of the field they were of the same energy, but now they will not be of the same energy. That would depend on the direction of the spin, and accordingly they would get say separated in the sense that degeneracy would get lifted. After that, you can apply a secondary radiation in order to have transition. So first we will see the interaction of a single spin with an external magnetic field. So we will start with this interaction of a single spin So single spin means, let me say you have one nucleus with spin I, or you have one electron with spin S. So 2 into I plus 1 number of spin states are degenerate. Here 2 into S plus 1 number of spin states are degenerate. Okay. So first, let's try to understand. So whenever you have this spin quantum number I, so there we talk about some I vector. This is the corresponding spin angular momentum, quantum angular momentum vector. Similarly, here electron spin angular momentum vector. So if I apply external field, let's say of strength B, this is the external field, then the corresponding Hamiltonian would be minus mu dot T. Okay. Here the mu is the magnetic moment because of the spin motion. Now here what we will see that there are two important characteristics associated with this. One is the magnetic property. It can be electrical property also when you talk about a start effect when you apply external electric field. But now resonance spectroscopy, I talk about only the magnetic field effects. So in this case, what is happening? Say when a body is spinning, it has two important physical traits. One, because it is moving, so it's a mechanical object, so it will have its own mechanical angular momentum. Second, because it's a charged body, so when a charged body moves, it creates some electric field, and whenever you have the electric field, that will have the induced magnetic field. So it will have its own magnetic field also because of that motion, and that generates the corresponding magnetic moment. So now you are talking about these two, and obviously they must be related because they are two different manifestations of the same spin motion, and we see that mu, which is the magnetic property, the magnetic dipole moment, by let's say spin, this is what is called gyromagnetic ratio. From the say nomenclature itself, you can understand. Say gyromagnetic ratio means you are talking about the gyration, that's the mechanical motion of the spin and the corresponding magnetic property associated with it. So this is for nuclei. It is Gn beta n by h cross, and for electrons we call G beta by h cross. Okay. So Gn is a nuclear, say, G factor. This is nuclear magneton. This is h by 2 pi. This is, say, this electronic G factor, or sometimes this is called Landau splitting factor also. And this is, of course, the Bohr magneton. And you write Bohr magneton and this as in joules per Tesla unit, say EH by 4 pi m joules per Tesla. So this is your nuclear magneton. And similarly, here you have the electronic mass that will give you the Bohr magneton. Now, we know this, say, properties, and from here we will try to find out the actual method of degeneracy of lifting and the associated transitions, so that in the next class, we'll be in a position to understand in a complex environment. Here we are talking about a single spin motion. So we know these values. Let me go back and check. So you have seen that I had written mu by I as gamma, and why I am writing this in terms of the you have the magnetic field, you have the magnetic property of the system. We try to go back to the mechanical property. Why? Because your states are written in terms of the mechanical property. So that means for a given I, you have I mi k's. Okay, and this I basically is connected to the corresponding spin angular momentum rather than the magnetic moment. So magnetic moment you can go via the gyromagnetic ratio, and I told you gyromagnetic ratio and what are the different forms of the attached quantities. And one important step, we know that if I operate I square on IMI, it will give you I into I plus 1 H cross square IMI. And if I operate IZ on IMI, that will give me MI H cross IMI. Okay, these are the two important aspects. If I operate I square operator, I get I into I plus 1 H cross square IMI, and IZ operating on IMI will give me MI H cross IMI. Similarly, I can write in terms of S square and SZ also. Algebra remains more or less same. Only you have to remember one is positively charged, another is negatively charged. So that is, and one is lighter, another is heavier. So these are the important differences that you know, but otherwise algebra remains same. So whatever I have written in terms of I will write exactly the same in terms of S, MS and S square, SZ, how they are operated. And these MI values can take the values from plus I to minus I to I plus 1. Suppose if it is a single proton, I is your half, MI can be plus half or minus half. We call them upspin proton and downspin proton. If you have electrons, then also I can talk about MS value plus half or minus half, whereas S value is just half, single electron. Okay. So here, if I want to calculate this extra energy I am getting because of this interaction, extra energy means this much you had the degenerate levels, and then I apply this extra field so that now I have, say, various stuff. So how do you differentiate this plus the expectation value of this much, so that this would be different for different MI values, and you get because of that difference. So when I talk about the expectation value of this, that means whatever extra in addition to this I am adding. Basically, this is the first order perturbation calculation of the Zeeman effect. And we have shown that the first order correction to energy, we did it in the last semester, is the expectation value of the perturbation Hamiltonian over the unperturbed states. So your unperturbed states are here. If I put the perturbation over here, apply external magnetic field of a given strength, and then we can show that this extra I can calculate. So now when I talk about energy, I mean that whatever I'm adding because of this interaction, that is the perturbation, and that is typically the corresponding, this is the Zeeman Hamiltonian. So that is the adding to the whatever remaining energy was there because of which you had the degenerate energy levels. In addition, now if you put this, and they will act differently on different MI values, and accordingly the energy will get, say, now the degeneracy will get different, and energy will be different. So let's try to understand that. How will you do this? So suppose I write B would be I dx plus j dy plus k dz. So this is the magnetic field, and the angular momentum vector also I can write I ix plus j iy plus k iz. Now suppose I apply the magnetic field only along a specific direction, axial magnetic field, let's say along z direction. So if I apply only along that, my B becomes only k dz, k vector dz, because I don't have any component along x and y. So what would be my, so mu dot B, here you can see, I can write from here, mu dot B becomes, the mu is gamma I, so gamma I dot B. So I have to find out what is I dot B. I dot B could be what? If I have B as only this much, what is my I dot B? Tell me what would be I dot B? If I apply the magnetic field only along z direction, magnetic field is only this. So this dot I. What do you get? The school level vector algebra. Tell.
So only the IZ BZ term will.
Okay, that means my Hamiltonian becomes now minus gamma Bz Iz. Is it okay? Minus gamma Bz Iz. Perfect. So now let's find out the energy. So energy associated with any IMIK. Again, what is this energy means? I told you that this is the Zeeman energy for any IMIK. That means you have to add this to the whatever energy was there for the degenerate set. So it would get lifted by this much of energy. This becomes IMI, considering my IMI to be let's say anyway, but I can put IMI later. So minus gamma Bz Iz IMI by IMI. So what would be the result? Iz operating on this, and you know what is gamma. So there is a minus sign, and Iz operating on IMI gives you Mi H cross. Then you take everything out, so they will get cancelled. I'm leaving 2 or 3 steps. Tell me what is the result. Do it and tell me very quickly what is the result. So it becomes minus Gn beta n Bz Mi. Because you had one H cross here, you get one H cross from here, they will get cancelled. That's it. Is it okay? Yes or no?
Yes, sir.
Okay then. So what it means is, suppose if I put the energy over here and Bz over here, the strength, when Bz is 0, two levels are degenerate. But mi can be half or minus half. Mi plus half will go down. So you have mi equal to half and mi equal to minus half. So you can see that alpha nuclear spin energy will go down and beta will go up. And what would be the difference? That would be governed by the strength of the external field. And now at Bz equal to 0, they were degenerate. There is no question of spectroscopy. But now for a given Bz, that would depend on the make of your NMR spectrophotometer, let's say. You can have a transition because delta Mi is plus minus 1. So you can go from here to here. So what would be delta E with that? What would be delta E for this transition? If I call delta E IMI, what do you get? You put Mi equal to half, put Mi equal to minus half, and subtract. Then what do you get? It would be just half plus half, 1. So this would be Gn, beta, and Bz. So you can see that how much frequency you require later to have the transition, that would depend on what is the strength of this Bz. So straight away you can see why it is called the resonance spectroscopy. So if I write this as h nu, I can find out, what is this frequency and how it is related to this. So this frequency would be more if you have this. Suppose if you go from 190 megahertz NMR machine to a 500 megahertz NMR machine, obviously the frequency required to have the transitions now between to Zeeman levels, they will also increase proportionally. Is that clear? Now we'll see the basic difference when you have the ESR spectroscopy. So this is the fundamentals of NMR with the single spin I talked about. In that case, you have, let's say, SMS. Only thing is, here you have one, extra minus sign coming because of the negative charge of the electron. You remember when I write EH by 4 pi MC, that charge E in case of electron, you have to put basically minus. Okay, and that will give you ultimately this sign will not be there. So E S M S actually would be G beta BZ MS. Okay, but G is now your Lande G factor, beta is your Bohr magneton, and this is the BZ and this levels. So the picture would be different now because there is no minus sign. So MS equal to minus half will go down. MS equal to plus half will go up. Okay, it is just getting reversed because of the charge. Okay, you have a negative charge over here. Not only that, this gap also for a given BZ could be different. So if I want to calculate, say, nu associated with or delta E, let's say delta E IMI versus delta E SMS. Okay, so in this case, delta E SMS is what? Delta E SMS would be exactly the same form. It would be G beta BZ. So if I want to calculate, so first the difference you could see because of the charge that in this case alpha goes down, beta goes up. Here beta goes down, alpha goes up. Now if I want to see for same BZ, the gap or the corresponding frequency, if I want to get, so what is the ratio of delta E IMI by delta E SMS? GR So this Gn and G, they are of order 1. Bz will get cancelled. So effectively it is the ratio of beta and beta n. So what do you get? Roughly, you see mass of the proton is around 2000 times. 1836 times more. So roughly 2000 times. So what do you get? The ratios of these two gaps, like this gap and this gap, for the same Bz. Tell me very quickly.
The mass of electron by mass of the nucleus.
What?
The mass of the electron divided by the mass of the capital N.
Yeah, I told you the roughly 1 is 2000 times. Then what do you get?
So ESMS is ESMS equal to 2000 into delta E IMI.
Yes, that means there is 3 orders of magnitude difference, and that is one of the reasons. So whenever you will talk about NMR, we consider megahertz NMR. Okay, 90 megahertz, 500 megahertz, 400 megahertz, megahertz. Whether ESR is always in the gigahertz region, isn't it? So NMR comes in the megahertz domain, whereas ESR comes in the gigahertz domain. If someone asks you what is the difference, don't go into anything spin, etc., etc. The difference comes only because of the mass. Okay? Do you understand? Yes or no?
Yes, sir.
Okay, so today I stop at this point. In the next day, we'll see a system, very simple system like hydrogen atom, where you have both electron spin and the nuclear spin, and how we can talk about that. So first, we'll talk about these two. Of course, you will have electron spin interacting with the external magnetic field, magnetic spin interacting with the external magnetic field, and electron spin, magnetic spin, like they're again 2 different magnets, they will interact, and that is what is called hyperfine interaction. So we'll talk about that, and after tomorrow that would be the last class, and after that 12th we'll meet for the exam. Okay. And I told you about the date, timings, and the syllabus.